Hello guys, in this video we will explore the convolutional neural network, aka CNN. Remember when we said in the standard artificial neural network that an input can be an image? Me neither, I had to go back and watch the previous video. Anyways, let's start diving. Why not a standard NN? How? All of these are valid questions, so have some patience and let's answer them one by one, starting with the what. Convolutional neural networks, commonly referred to as CNNs, are a specialized type of neural network designed to process and classify images. So basically, a more advanced neural network, and we know that more advanced equals more complexity. Why is being a neurosurgeon more advanced than a family doctor? Because it is more complex. Okay, now why not just use a normal artificial neural network? To answer that, we need to understand what an image is. An image is a bunch of pixels, which are just small units of color, and the color itself is an RGB number. Did you know that all the different colors and shades can be expressed as a mix of red, green, and blue? Congrats, now you know. Now that we know that an image is a bunch of numbers, why don't we just use an artificial neural network? There are a lot of reasons, but the main two are: first, high dimensionality of images. For example, a 224 times 224 RGB image has 224 times 224 times 3 equals 150,528 pixels. If we feed this directly into a normal NN, each pixel is one input neuron. The first hidden layer, with just 1,000 neurons, would lead to 150 million weights. The second reason is that spatial structure is lost because fully connected NNs treat each pixel independently. We would lose the context that is very important, or we can just say that pixels in images have local patterns. For example, this beautiful woman, according to my type, of course. We can't just recognize that there is the color yellow. I am talking about her hair. We want to recognize that because the yellow is on top of her forehead and near her eyes, we understand that it's hair, not just a random yellow patch. Okay, so now how can a convolutional neural network fix these problems and be a more suitable approach for these types of problems? We will do some operations that would extract the relevant features that we would then pass to our fully connected layer, aka good old neural network. So naturally, the next question is, what are these operations? So the first thing that you need to do is to stop asking me questions that I am going to answer anyway. Second of all, let us start with convolution operation. The convolution operation involves multiplying the kernel values by the original pixel values of the image and then summing up the results. Original pixel values are the input image. The kernel value is a small matrix of numbers that will help us detect local patterns, edges, corners, textures. For example, in this handwritten 7, we can see that applying the convolution operation starts detecting the important pattern. These kernel values start random, as you may have expected, and then they get updated in the training process, just like weights and biases. I hope that this animation helps. It is not mine, of course. It is important to note that there are 3 essential components inside convolutional layers: channels, stride, padding. A channel is basically the depth of the input. A 24 times 24 colored picture has a depth of 3, 1 for each color, as we said in the beginning, but a grayscale image has 1. The stride represents how far does my filter jump. From this GIF, we can see it is 1 at a time. Padding, how do we handle borders? Look at the GIF and notice that we are adding data sometimes at the top, left, or right of the input for it to match the kernel or filter size. Feeling lost? This slide will help you understand. I will count to 20 silently to give you time to understand. Take a 30-second pause because I love you. Now for the activation layer or operation, we generally use ReLU in CNNs to add nonlinearity. I won't dive much here because we talked about it in the neural network slides. Remember that we said that CNN extracts the relevant features that we would then pass to our fully connected layer, aka good old neural network. So how do we make a large image smaller, but keep all the important features like edges and colors? We do that in two ways, either by grouping a group and getting their max or by getting their average. Note that in pooling, we are not applying any kernel to the input data. We are just simplifying the information with a math operation, max or average. You can see how each pooling layer is reducing the dimensions of the spatial space, but it's not reducing the number of channels. Now let's read what SpongeBob has to say in this matter. In a CNN, we can stack multiple convolutional and pooling layers before reaching the fully connected part. Each layer learns increasingly complex features, from simple edges to shapes, then to full objects. The more layers we stack, the deeper the network's understanding becomes before the dense layers make the final decision. After convolutional and pooling layers have extracted relevant features from the input image, we have to turn this high-dimensional feature map into a format suitable for feeding into fully connected layers. Here, where flattening layers come into action, it takes the entire feature map and reorganizes it into a single, long vector. Wait, did we just change the shape of the data? I thought that was a criminal offense. It's okay, relax. Although flattening changes the shape of the data, it does not make any changes to the actual information. Think of it like this. After the CNN layers, we're done detecting features, now we just need to reason about them. Flattening simply reshapes the data so a normal neural network can take over. After several convolution and pooling layers, we pass the flattened data to a normal neural network, fully connected layers, which performs the final decision or prediction based on all the features the CNN has learned. And of course, we don't forget the activation functions. Finally, yes, finally. Forward and backward pass in CNN training. Forward pass. The image passes through all layers. Convolution right arrow activation, right arrow, pooling right arrow, flatten right arrow dense. The network produces an output prediction, e.g., cat or dog. The prediction is compared to the true label using a loss function, measures how wrong it is. Backward pass, backpropagation. The network calculates gradients of the loss with respect to each weight, including filters. These gradients flow backward through the layers, adjusting weights and biases to reduce the loss. Now subscribe and like the video. Bye.